Now we welcome a presentation on maximizing the performance of a BEV rear twist beam suspension with Alejandro Garcia Osorio, chassis simulation engineer from Applus IDIADA, and Vikraman, head of vehicle mechanical systems at Mahindra and Mahindra. Discover how a pioneering approach based on the integration of Atom's real-time models into IDIADA's DiM250 driving simulator revolutionizes suspension tuning for electric SUVs.
My name is Alejandro Garcia. He's Vikraman, and we'll present the topic for you, so you can start whenever you want.
Of course. So good evening to everyone over there. Can I get the slides up and running?
They're visible. Yeah, next slide.
Good. Okay, can you just get the camera so that I can see the slides?
What do you mean, sorry?
Yes. Yeah, I'm able to see now.
Okay.
Okay, so good evening to everyone. It's been a great pleasure presenting our innovative approaches in this VI Grade Zero Prototype Summit. Mahindra and IDIADA, we have a long partnership already, and we always come together to provide some solutions to complex problems. And you know Mahindra very well by this time. We are a very strong brand in sports utility vehicles in India. We are very strong in ICE, and now we are making some world-class battery electric vehicles. We are, I would say, one of the pioneers along with IDIADA to leverage the potential of drive simulator to reduce the dependency on the physical testing and take some critical decisions during the simulation phase itself. And we have tasted a lot of success in the past using the drive simulator. In fact, in the recent past, we have launched so many vehicles with world-class ride and handling. The Indian market is very difficult, as most of you would already know. We have varying road conditions, and the customer expectations, they keep rising every year, and providing a solution which is expecting the ride and handling expectation of Indian customers in varying road conditions is extremely difficult. And I'm glad to inform all of you, along with IDIADA, Mahindra could develop these kind of cars and launch successfully in the market, and they are very well received in the market. So in the recent past, we launched XUV700 and also the Scorpio N, and also very recently the XUV400, which is our first battery electric vehicle. And as usual, we leveraged the drive simulator, extensive simulations, and we worked together to provide the solution to these complex problems. Next slide, please. So all of you maybe already knowing what is Mahindra and Mahindra as a brand. So we are more than a $30 billion company as a Mahindra Group. And within Mahindra Group, Mahindra Automotive is a very strong company. We make world-class SUVs, mostly in Indian market and also some global markets. Very big R&D center we have in Chennai, which is Mahindra Research Valley. And of course, we partner heavily with IDIADA, who are the pioneers in vehicle dynamics development. And also they support us in so many other proving ground and validation and crash development and so on. So our partnership has been growing from strength to strength over several years. And also our partnership with VI Grade and with this, especially this Zero Prototype Summit, also has been growing from strength to strength. So to speak, 2022, we presented the development of XUV700, how we used the drive simulator to reduce the number of iterations and provide world-class ride and handling. First time we introduced frequency-dependent damping. First time we could develop successfully a controlled blade-type suspension for a very high-end SUV. And also in 23, last year, myself and Guido, we presented how we integrated a semi-active suspension model successfully in drive simulator, and how we could select what is the valve code and what kind of control algorithm that we should have, so that we are able to reduce our development time in the proving ground. And now, in our journey of excellence, we are taking it to the next level. So this time the problem is, how do we optimize the rear twist beam for a battery electric vehicle? It might sound to be a very conventional problem, but a battery electric vehicle of more than 1.7 ton or more than 1.8 ton curb weight and 2.2 ton of GVW, the gross vehicle weight. For that kind of a car, how do you design the rear twist beam so that we are able to give a very good stability without affecting the ride, the pressure ride, which is very, very important for the Indian customers. So the new platform, what we are trying to develop is a completely a new, let's say, battery electric platform. It will be predominantly front wheel drive, and the steering rack is gain the powertrain as usual. It will be having boasting a 19-inch tire. This is a representative image. We are trying to, we already launched this car, but we are developing a new platform with all these attributes. The front will be a very conventional McPherson fully independent suspension. And most importantly, the rear is twist beam. And you know why we are going for this approach? Because the Indian market is extremely cost sensitive. So they want to have, I would say, in terms of the functional attributes, everything best in the world, but at an affordable cost. So this is where the innovation has to come in, and all the extreme development approaches which can guide us in this path to make this rear suspension successful with this kind of architecture and still able to deliver a very good stability even with a very high curve weight. As you can see, it is 1700 kg because of the battery, which can be starting from 40 kilowatt hour up to 60 kilowatt hour this platform can support. And as you know, as a brand, we are playing in sports utility cars, which means our center of gravity height will be always higher than the benchmark. So your roll moment arm will be higher for the given lateral acceleration. Your roll moment will be higher. We have to make sure that the rear suspension is perfectly developed so that we are not ending up in any issues during the physical vehicle development. Coming to the rear twist beam, why it is so important? In fact, when we started this project for a battery electric vehicle of this category with 40 to 60 kilowatt hour battery with the rear twist beam, there are not a lot of benchmarks available all over the world. Most of them are ICE converted EVs, and it is a kind of the ICE suspension is taken and tuned with some stiffer spring and increased damping forces, and it is more of a the platform is already there, and the battery is packaged in whatever space available, and the suspension is retuned. This is the kind of vehicles that we could find in the market, but there is no born electric platform available in this configuration. So this is the problem that we are trying to solve. So there is no benchmark available. So Mahindra and IDIADA decided that, okay, let us create our own benchmark. So the objective is very clear. It's a simple and cost-efficient solution. You know that the moment I have the powertrain in the front, with respect to mass distribution, I get an advantage. The vehicle is already going towards the understeer. So I have to take that advantage and reduce the cost in the rear suspension. However, the overall mass of the car is a challenge. It is more than 1.7, 1.8 ton curb weight. And when 5 passengers are sitting and along with the payload, it is going beyond 2.2 ton, right? The other thing what we are trying to solve is within the given wheel track, how do we maximize the motion ratio? For example, in the Y direction, can I assemble the shock absorbers and the springs in a way that I'm able to improve the motion ratio so that with minimum spring stiffness, I'm able to get maximum low stiffness. But there are a lot of disadvantages of the rear twist beam, as you might already know. First of all, when there is a lateral force that is getting generated because of the slip angles of the tires, you tend to get some amount of lateral toe compliance. This is inevitable in case of rear twist beam because entire thing is swinging about the bushes, and the bushes will have some conical stiffness. So when there is a lateral force, you normally end up with some kind of a toe compliance, which is very, very dangerous, and that might take the vehicle into oversteer and lead to stability problems. So this is one of the biggest thing that we need to solve. And when I try to make the bush very stiff and try to solve the lateral toe compliance, then automatically we have to compromise the longitudinal complaints. That will have a penalty on the ride. So it's a very, very strong trade-off between ride and handling whenever we try to develop this kind of rear twist beam suspension. In a control blade 4-link suspension or a 5-link suspension, I have a lot of degrees of freedom in terms of hard points, and the lateral support is quite good. There is a lot of flexibility in terms of bushing stiffness. Different links are different, doing different tasks, whereas here everything is intertwined. So now, how we partnered with IDIADA and how we used the drive simulator. How did we, optimize this system by optimizing the shear center, by investigating the correcting bushes, and completely making an MNF model and integrating with the drive simulator, and doing all kind of optimization, multiple iterations, how we could achieve the required performance. That will be explained by Alex. So over to you, Alex, and thank you so much.
Thank you very much. So, well, that looks like an Italian flag, actually, so never mind. Yes, it's very obvious at this point that we need virtual development to help us to develop this kind of suspension. However, we still face some issues in there, so it's not that easy. We mainly face two issues in the virtual development process. First of all, we want to be fast, but we have so many things to tune in a twist beam. Let me give you an example. You have a twist beam here, and you can play around with the hardpoints. You can also play around with the cross beam, so you can try different shapes, you can try different orientations, you can try different positions, and that will give you different performance. And besides that, you have the bushings. So you can play around with the stiffness, you can play around with the bushing orientation. And there is an issue here because most of these parameters cannot be tweaked on a flexible body. So we need to overcome that. And for that, one of my colleagues, João Monil in IDIADA, came up with a brilliant solution, which is a hybrid concept twist beam model. Besides that, we have another problem. When we compare models from MBS to parametric software, we kind of lose performance. Especially with flexible bodies, we lose some performance and the control of the flex body, what it's doing. So to overcome that, we decided to go for Adams real-time. First things first. What is the twist beam concept model? Well, we have two different approaches to model a flexible rear axle like this in Adams. First one is the model neutral file. This is the most common approach. It's just a flexible body, which is converted from a CAD file. And it has a clear advantage. It gives you accurate performance, that's for sure. However, as we talked about, we have a lot of parameters to tune, and we don't have the room for tuning here. And also, it's a pretty time-consuming task to generate those files. So there's another approach, which is similar to what anti-roll bars look like on Adams, which is the beam element modeling. This is good because it gives you some freedom, actually gives you a lot of freedom. However, there's a main drawback here, which is that it doesn't allow to simulate cross-open sections. And for a twist beam suspension, that's really an issue, because you want to have your beam member probably as an open section. And besides that, you need to be very specific and very accurate with the properties of the cross beam itself. You have different sections for the trailing arms, for the cross section. You need to know that very well and implement it very well. So the solution for this is to combine both worlds to come up with the twist beam hybrid concept model. This gives us the best of both worlds, because now we have a parametric design. We have a flexible MNF cross member, so we can put there whatever shape that we want. We connect it through a hardpoint to the trailing arms, so now we can study many different configurations. And we also have the hardpoint freedom, so we can put the hardpoints whenever we want. And that gives us infinite possibilities to study. Besides that, we have an accurate performance. Let me show you some examples. You can see how kinematics and compliance and the full vehicle maneuvers look very similar when comparing this model to the corresponding beam 1. So the beam MNF. How do we fit this into our development process? How does it help us to improve efficiency? Well, let's say we want to go from the performance status of a beam. We want to improve that to come up with a solution for the driving simulator. We have to make some proposals. And those proposals have to be based on theoretical knowledge, experience. After that, we can ask the CAD team to generate the MNF files. And then we can be able to validate the results. However, it's very likely to happen that we have to come back to the start, because probably we didn't end up with what we wanted to go with to the driving simulator. So by the time we go there with something that's worth a shot, for 4 different iterations, for example, it would take us about 3 weeks. However, if we include this model here, you can see how now we can iterate in that phase, and we can ask exactly the MNFs that we want. So we save a lot of time, we can go to the driving simulator much faster, and we can also use the model there. So we can iterate live with our driver and just get the feedback from him and change the beam position, the hard points, whatever we want to test. So that reduces 70% the development time. That's pretty good reduction, actually. So that kind of solves one part of the equation, but we're still missing one bit, which is how do we go from Adam's model, from multibody model, to the driving simulator without losing any performance, any accuracy? Well, we typically go for an MBS model. We do the model conversion. We have typically a car real-time model. And after some troubleshooting and some correlation work, we end up with something that can go to the driving simulator. However, again, this is time-consuming. And apart from that, for this specific case, where we have this type of suspension, which is very dependent on the flexibility and the structural characteristics of the beam itself, it's not what we want to have. We want to have full control. And let me just highlight here that it's on this time that we're skipping car real-time. I love car real-time. I want to be invited to this event again, so just for this particular case. So now we can go from Adams to the driving simulator. What advantages that gives us? We now have a fast process, because you just put some communicators in, put the model in the driving simulator, boom, easy to drive. It's also an accurate performance, as I'll show you in a minute. We can include the flexible bodies. So we can put, I wouldn't say as much as we want, because there's a limitation, but at least for the twist beam itself, we can include it in the model, and that gives us quite an improvement in performance. And besides that, we have the possibility to tune many different items, springs, dampers. If we use the concept model, we can even tune the beam on real time. So we don't have even to stop the motion of the driving simulator to change the parameter. And that's pretty impressive, actually. So objectively, that's how it looks like. The red line and the blue line are the 2 Adams models. Blue one is the Adams model when we run offline simulations, and the red one is the Adams model run with the different solver settings that we need for real-time simulation. And then the green one, and sorry for that via grade, that's car real-time performance. Well, you might think there's not too much of a difference here, even though I think it's pretty clear. But let's see what our drivers feel. In terms of the feedback that we received from the drivers when testing this model, the body control was much better. They were able to perceive the roll motions much better in a more damped. The dampings of the system were more closer to the real vehicle. Besides that, in handling, they were also able to feel the compliances much better. Compliances, delays, the overshoots, pretty much like a mechanical system would behave. Then, in terms of ride comfort, obviously, just putting the flexible body with its vibrational modes and everything there, they're able to feel higher frequencies. And also, they were much more able to differentiate between primary and secondary ride. And last but not least, in terms of steering, they could feel a more realistic torque buildup and a better system damping, which comes from the fact that now we can use the steering maps damping EPS that we use in Adams straight into car real-time. So, to sum up, how does this help us in our development process, in our journey to enhance the performance of this twist beam? Well, we started with about 70% of metrics in terms of KNC metrics achievement. Now we've gone up to 91% overall metrics accomplishment. And we have been able also to fine-tune some key items in vehicle response, like the response delay, the roll dampings, the agility of the vehicle. We are now pretty much on targets or very close to them. And I will give you some data that combining the concept model with Adam's real-time has allowed us to achieve. It's been 6 months of the development process. We have tested more than 25 hardpoint settings, more than 20 cross-beam layouts, of more than 8 or 9 cross-beam designs, and 10 bushing configurations. During this time, we have hosted 4 driving simulator sessions, on which we have tested more than 20 vehicle variants, and we have validated 5 concept models, comparing them to the corresponding MNF model. And all of this, we have achieved all of this with the impressive amount of 0 prototypes. Thank you very much. Grazie mille. If you have any questions, feel free to ask.